So next presentation comes experience in Japan. It is devoted to application of singular integral equation to break moving near an inclusion in two-dimensional plate. The speaker is Dr. Masayuki Sanai. Is that correct?
Yes, pronunciation. The title of my presentation is Application of the Singular Integral Equation and to the fact moving inclusion in the two-dimensional elastic infinite plate. So I'm Masayuki Arai from the Tokyo University of Science. The host of this presentation is Kazuki Yoshida, who was at graduate school in the University of Japan. Oh, yes. The fatigue plug is often initiated in structural component as shown here for the long-term operation as shown here. So sometimes that's the worst scenario, the catastrophic damage is occurred in structural component as shown here. So in order to extend the lifetime of the structural components, that we need to do that repair for the damage of structural components. So you know that there is a precipitated inclusion method, which is one of the repairing technique. This technique is based upon the flak propagation deflection by inserting the inclusion into the circular hole, heteroplactive. So, but there is some main problem. So where we put this pressurized press-fitted inclusion in the heteroflective. So it is needed to calculate the precise rate stress intensity factor that give a plug in the inclusion and plug propagation bus geometry. This picture indicates the elastic spike with the thread pack and the press-fitted inclusion, which is subject to the tensile P of it at the far field in these cases. For evaluating the stress intensity factor for these cases, that we need to, we have interested in the continuous distribution dislocation method. So in this method, the edge dislocations are distributed around the particle plug as shown here. And then for deriving the stress intensity factor, the problem was is superposed with a problem result plug with the same geometry. By formulating this problem, we have a singular integral equation. And also by solving this singular integral equation, we have a dislocation density function. Using that, we can evaluate the stress intensity factor to our problem. And also, using this stress intensity factor, so we can predict the plug propagation geometry for problems. However, it is difficult to predict precisely the plug propagation path using that. So the purpose of this study is to develop a new algorithm for simulating the plug propagation geometry based upon this continuous distribution dislocation method. So this picture indicated the elastic media with the hole with a radius area. So by inserting the circular hole of the radius A plus epsilon into this hole, we have a residual stress around here. So for situation, the global coordinate x and y is set at the center of the precipitated inclusion, and also local coordinate xk and yk is set at the center of the precipitated inclusion as shown here. So it should be noticed that the local coordinate xk is rotated from the x with rotating on psi k, and also the plug, the xk is parallel to the plug as shown here. So from the local coordinate xk and yk, the tip of the plug is located at the bk to ck and the xk on the x-axis, xk axis, and also hk on yk axis. So, and then this media is subject to the tensile, the far field. For solving that, we divided into three auxiliary problems as shown here. The first auxiliary problem indicated the problem, auxiliary problem indicated the inclusion, which is subject to the tensile of the far field. The second one indicated the precipitated inclusion. And also the last auxiliary problem is the elastic plate with the inclusion and the distributed edge dislocation as shown here. So by taking a summation of the auxiliary problem, so we have the stress field, the stress intensity factor for these cases consequently. So that tractions around the body of plug line can be derived from here. For example, this line indicated solution for the first auxiliary problem, and second line indicated the second auxiliary problem, and also the last line indicated the last auxiliary problem solution. So the summation of the traction around the particular plug line should be 0 for implying the traction around the particular plug line. So yes. And then by doing that, we have the rational equations from here. So in this rational equation, this term is very important because this is the fraction caused by a dislocation distribution. So which is expressed by this equation. So where the fxk and fyk as a dislocation density functions, and also k1, k2, k31, and k32 are influences functions which are related between the point xk and the point x psi k as shown here. So we need to solve this equation for under the arbitrary boundary conditions or not. So by formulating this equation, we have the consecutive singular integral equations on here. So in this case, in this study, that this term fxk, fyk was converted to this equation will show the singularity at the tip of the track. And also the integral interval bk to ck was also converted to the normalized interval minus 2 and 1 by using this equation. Finally, we have a normalized singular integral equation as shown here. So for discretizing the singular integral equation, interval minus 1 to 1 divided by 2 times as shown here. By doing that, we have the unknown function of the dislocation density function. That number was related to the 2 times 2 and plus 1. And on the other hand, number of the equation for the stress singularity equation were 2 times 2 in this case. So for compensating for this insufficient equation, we need to consider about the another condition. That is the Plankov displacement as shown here. This integral equation indicates the component of the Plankov displacement. So by using this, we have the condition of dislocation density function. Using that, so we can solve the completely the stress intensity singular integral equation. That singular integral equation is extended to the curved plug line as shown here. So in this case, the curved plug line was divided by using the straits, so which already shown here. And then also each is this straight plug called subplug. So in this study, and also each straight subplugs is parallel to the local coordinate xk axis as shown here. For deriving that the singular integral equation, the curved plug was divided by as shown here, and also each dislocation were distributed around the discretized curved plug line. So and then the traction due to the dislocation distribution is extended to the subplugs at the arbitrary position by acting the rotation matrix. That the rotation matrix can be expressed in here, where the psi is a rotation angle between xkx and xk axis. And then by solving the singular integral equation with additional function related with the Plankov displacement, so we have the edge dislocation density functions here for at the left tip of the track and also the right tip of the track. So by using that, so we have the stress intensity factor at the both tips of the track as shown here. So by using that, so we developed the new algorithm for simulating plug propagation. For simulating the plug propagation, we developed about the probing methods on here. If the straight plug is existed in the elastic media as shown here, the tip of the plug is extended with the increment length of the plug d eta and probing angle alpha. So we need to adjust the probing angle to such to minimize the modular stress intensity factor. And in this case, this probing boundary is restricted under the probing ranges. And also to the clock propagation direction is cited under this preliminary. So which implied which means to imply that the minimum wise of the mature stress intensity factor. By using this algorithm, so we searching the best position of the tip of the clock tips, and continuously we do the calculation, and we finally we get the clock propagation deflection on the computer by using the program which was proposed in the study. Let me show you some small results by using this probing methods. This is analysis condition here. And so in this case, the action was set to be was changed from the plus value to the minus value under the combination of Young's module here. E1 indicated the AR6 media, and also E2 is the Young's modulus of the circular projection here. And then the clock is located in here. This media is subject to the tensile load here. The tensile load was assumed to be 100 megapascal in this case. And also, another case is that we change the combination of Young's modulus between the circular plate and the elastic plates. And then the fixed condition of the epsilon. This then indicates the parameter for the probing method. The barrier, for example, the beta, that is like the beta length. Plug length was said to be 0.25 millimeter, and also the that is the incremental length was said to be 1 meter, and then T, that is the probing range was, and that 40 degree, finally, the tolerance, that is the differences in the multi stress factor between the left tip and right tip, that was seemed to be plus minus 5.0 megapascal root square millimeter. So by using that, we simulate it. Let me show you some pretty small results for that related with the clock propagation path geometry. This is the straight line gets the clock line. So by using this model, we do the calculations to simulate the clock propagation path geometry. In these cases, we consider about the influences of the epsilon. When we change, when epsilon is including action here, the tip of the clock tip is goes to the precipitated inclusion in this case. But this is very interesting, the results, because if we change it minus epsilon cases, the tip of clock goes away from the precipitated inclusions on here. When we consider about the pressure interfaces between from the circular plate to the elastic plate, so when epsilon is included, this value is also increasing, as shown here. Maybe from this result is that the pressure changing is strongly affected to the clock path geometry, as shown here. So, and also we consider about the influences of Young's modulus here. The epsilon was fixed. And also we change the Young's modulus combinations in here. In all cases, the tip of clock tip is approaching to precipitated inclusion. However, if the Young's modulus of the circular plate is sucked than one of the circular elastic plates, so the tip of clock is more increasing. So it's all result from the results, and the result that it was confirmed the epsilon, the Young's modulus, and the inclusion have a big influences on the clock propagation path geometry. This is a conclusion. The new algorithm for rating the clock propagation based on the continuous distribution dislocation method was developed. So in this study, we proposed about the probing method. This is the automatically we simulated that on the problem. And also, we treated about this kind of the problem by using through those results. So the appropriate inclusion position can be decided by this probing method. This is a very useful where we put the precipitated inclusion. So that is which position is the best when we repair damaged components. Thank you so very much for attention.